Hello everyone, welcome to the International Conference on Analog VLSI Circuits, AVIC 2021. My pleasure, François Rivet here in Bordeaux, to welcome you all with my co-chair, Kari Sekine.
Yes.
So we'll switch on the slides. And I will give the floor to Kari.
Yes. Good morning, everyone in France, and good afternoon, everyone in Japanese. I'm Kaori Sekine from Meiji University and General Co-Chair of AVIC 2021. It is a great pleasure to open the AVIC International Conference on Analog VLSI Circuit. This time, the conference is held with hybrid mode. Although I cannot meet all of you in person in Bordeaux, France, I believe everyone will have a lot of fruitful time thanks to the online systems. I'd like to introduce General Co-Chair here, Professor François Rivet from University of Bordeaux. He has put a lot of effort into preparing AVIC 2021. I'm very grateful to him. The International Conference on Analog VLSI Circuit, AVIC, is a successor of International Analog VLSI Workshop. It has been held for more than 20 years. The workshop was initiated by the research committee of Electronic Circuit of the Institute of Electrical Engineers of Japan, IEEJ. The first workshop was opened in 1997 in Columbus, Ohio, United States of America. Since then, it has been organized in cooperating with a selected host country each year. Like the workshop, the purpose of the AVIC is to provide the international stage for students, professors, and researchers, and also industrial specialists in the field of analog VLSI. The aim of AVIC is to exchange ideas and recent results, and as well as their applications. For a long time, it has contributed to worldwide community of analog VLSI circuit experts in industry and academia. In this time, we are very happy to open AVIC 2022-21 in Bordeaux of France. In spite of the difficult situation due to COVID-19, AVIC in Bordeaux is second time. The first was held in 2005. At the time, Professor Yann Leval from University of Bordeaux and Keitaro Sekine from Tokyo University of Science were the general co-chairs. We are honored to be the general co-chair in this time. Many thanks to all the professors and researchers who have been supporting to AVIC. The second AVIC in Bordeaux has been realized. I'd like to hear some comment word from Professor François, the General Co-Chair of AVIC 2021. Please.
Thank you very much, Professor Kari Sekine. So first of all, I would like to thank a lot everyone to attend this conference. We have 121 attendees registered last Friday, with 35 persons here in Bordeaux and 86 in virtual. I've written, well, in French, merci, and in Japanese, I think it's arigato. Arigato gozaimasu. And I would like to thank everyone. I would like also to thank all the committee who have contributed to make this conference. So here are listed all the names of those who participate to the organization of AVIC 2021. I would like also to thank all our sponsors who contributed to help us financially and to make the conference visible, as well virtually and also in person. And as you know, we have worked a lot for excellent social events. Now I leave the floor to the TPC chair, Satoru Shingai.
It's okay. Good morning, good afternoon, and maybe good evening or good midnight to somebody. If there's somebody in midnight, very sorry about that. This is AVIC Technical Program Committee Chair. My name is Satoru Shingai from Canon Incorporated. First of all, I deeply appreciating the huge effort of the AVIC France team to open this AVIC today, even if the last year canceled because of the acute COVID infection worldwide. Many thanks. And also, many thanks for the big effort of many others of France, Japan, the other countries to submit the many papers under this situation. We decided to hold this AVIC, including the online virtual, while international travel is still restricted. However, I believe our opportunity will attract more participants to AVIC, and the discussion in this at this AVIC will become more active because of more participants, hopefully. And I hope that all the participants will get to AVIC channel for the future activities, and through the your active question and answers to share the topics. I look for your contribution until at the end. That's all of my greeting. Thank you very much. That's it.
Thank you very much for your words. So we will start this conference with a keynote speech. The very first one will be from Dr. Ryuichi Fujimoto this morning. And also you have two other keynotes tomorrow and the day after, one from Dr. Keith Odenug and last one from Victor Greenblatt. Also, we have invited talks, one this morning by Professor Eduardo Charbon, who is here in person and will provide his talk virtually, and tomorrow by Professor Jan Rabai. Now I give the floor to my colleague Marina Deng to explain you all the details about the program and the social events.
Thank you, François. Okay. Hello, everyone. My name is Marina Deng. I'm the General Co-Secretary from Bordeaux, and I will say a few words about the program and the venue. So the conference runs from Monday to Wednesday for technical sessions, keynotes, and invited talks in mornings, and there will be the student event on Thursday morning. The proceeding can be downloaded online from the website with a very easy password. Okay. Regarding the venue, the conference will be held here in IMS Bordeaux, University of Bordeaux, which is located in the south of Bordeaux City. For in-person attendees, the presentations will be given in the amphitheater here. And for technical sessions, because there are two in parallel, we will use also a room Délibération des thèses, which is very near by the amphitheater. For virtual attendees, please use the links provided online, YouTube for keynote and invited talks, and Zoom for sessions. For the lucky people in person, we will have lunch every day together. We'll go to the restaurant La Passerelle with a 3-course seated meal to discover French gastronomy. And during 1 hour and a half, we'll take time to exchange and get to know each other. We'll go there by tram. The tickets will be provided by the conference. Departure will be at 12 p.m. from the IMS lab. Just follow Rémi, Maxine, and Vicente, with the organizers and students. They will guide you from tram stop Pexoto to Toyambus. And tonight we'll have the social event, the welcome reception at 5:30 p.m. in the hall of IMS. And the cocktail and buffet service will be waiting for you to taste local products. After that, there will be options to enjoy dinner in local restaurants. And last but not least, tomorrow there will be the gala dinner with cultural event at Château Pape Clément in Pessac. We'll start with the visit of the winery, wine tasting, cocktail, and we continue with the gala dinner, a 4-course French meal with wine pairing, and with a very nice view on the vineyards. So how to go there? We'll use a bus. The departure will be at 5:30 p.m. sharp from the IMS lab, and the return at 11 p.m. from Château Pape Clément up to Forum tram station. So on behalf of the organization committee, we'd like to warmly thank you for your participation to AVIC 2021. And we hope that you will enjoy the conference as well as the social program made for you. Thank you very much.
Thank you very much, Marina. So we are perfectly on time. And now we will switch to the first keynote. And I will give the floor to my colleague, Professor Kaori Sekine, to introduce the keynote. So we'll switch the screen. Connecting.
Yeah, I start. I can start. I'm connecting now.
The slides. Could you share your slides, please?
Oh, yes. Okay.
Yes. Now let's start the keynote session. And the title of the presentation is Technical Challenges Toward High Bandwidth and Large Capacity Storage with Low Power Consumption. And is it ready, Professor? Yes. And I will introduce Dr. Ryuichi Fujimoto. He is Senior Fellow of Kioxia Corporation. He was engaged in the research and development of integrated circuit and device modeling for various wireless communication systems in Toshiba Corporation. After belonging to Kioxia Corporation, he manages research and development of high-performance interface for NAND flash memories. Dr. Fujimoto was a chair of the Japan chapter of IEEE Solid-State Circuit Society. And please start your presentation.
Okay, Professor Sekine, thank you for your kind introduction. Can you hear my voice?
Yes, but I can't see your camera.
Oh, sorry. Can you see? Only slide showing is okay for you?
Yes, slideshow is okay. Your face is not shown. Yes.
Okay. let's start my presentation.
はい。
Bonjour, good afternoon, everyone. This is Rich Fujimoto from Kyokushia speaking. It is my honor to present keynote speech at ABIC 2021. And I am a little sad because I cannot join ABIC. This is the outline of my talk. Some may not know about our company Kioxia, so I will introduce briefly about our company at the beginning. Next, I will talk about the background of my talk and some recent technical trends. After background and trends, I will present about our development for high bandwidth and large capacity storages. After that, I will show one issue about differential transmission line on low-cost printed circuit boards (PCB). Then, I will talk about our scope of future works briefly, and finally, I will present my conclusions. Okay, let us start with introduction of our company, Kioxia. At first, our company was a part of Toshiba Corporation. In 2017, Toshiba Memory Corporation was established and separated from Toshiba. And in 2019, Toshiba Memory rebranded as Kioxia Corporation. The name Kioxia is a combination of Japanese word kyoku and Greek word axia. The Japanese word kyoku means memory, and Greek word axia means value. These two words are combined, and the name Kioxia is created. Main products of Kioxia are NAND flash memories and solid-state drives (SSDs). In past days, NAND flash memories have planar structure like CMOS technology. Recently, NAND flash memories have three-dimensional structure to achieve large memory capacity, like this figure. This photograph shows fourth generation products with 96 layers of NAND flash memories. Our current generation product has 128 layers of NAND flash memories, and the future product will have beyond layers. This photograph shows our USB memory product. We also have solid-state drive SSD products using NAND flash memory like this figure. The sales of Kioxia is about $10.7 billion. It is about 1 兆円. This sales is in the worldwide top 10 semiconductor company, and only one Japanese company in the worldwide top 10. The worldwide number of employees is about 13,000. There are many people with various backgrounds. Because Kioxia is a memory company, there are many memory device engineers in our company. But many engineers in other technical areas, analog and digital circuit design, network architecture, security, deep learning, and so on, also works in our company. Our sites are in 10 countries and regions. We have a large plant for NAND flash memories in Yokkaichi, Japan. Some research and development sites are in Yokohama And now we are constructing new research and development sites in Shinkoyas and Ofuna. Now, let us move to topics on background of our works and some technical trends. As you know, global amount of data is continuously increased. Now, global amount of data is expected to be 80 zettabytes in 2021 here. It will be increased 180 zettabytes in 2025. We have to write and read such huge data, large capacity and high bandwidth storages are strongly required. In other hand, per consumption of worldwide data centers is seriously increased. Now it is 200 or 300 terawatts hour, and it is expected to increase up to 400 or 1000 terawatts hour in 2030. Current per consumption of Tokyo is 100 terawatts per hour. Compared to the per consumption of Tokyo, the per consumption of data centers is very, very large and it should be reduced. To reduce per consumption of data centers is one of key mission of Kioxia, I believe. This slide shows communication network with various communication distance. For long distance, such as long haul and wide area networks, optical technology using optical fiber are utilized. On the other hand, for short distance networks, such as local area network, interboard network, and interchip network, electrical technologies using copper interconnect is used. Today, I would like to present both optical and electronic technologies. This slide shows a relationship between modulation scheme and data center interconnection DCI distance in the optical networks. For short DCI, such as inside data center and DCI between two campuses within 10 kilometers. Here, IMDD is used. IMDD is intensity modulation direct detection. It means NRZ like this and palm hole for level pulse amplitude modulation like this figure. On the other hand, for long DCI between two metro area or long haul terrestrial and undersea of over 600 kilometers, coherent is used. In the optical community, the coherent means quadrature modulation scheme, such as QPSK and QAM. For middle distance DCI, IMDD or coherent is used. One of technology attracting recent attentions in the optical community is silicon photonics. In case of conventional optical unit, shown here, many bulky discrete optical components are needed, and large area such as a desk is needed for them. By using silicon photonics, we can integrate the optical unit in the tip. Silicon photonics is SOI CMOS-based semiconductor technology. We can use optical waveguide in the silicon photonics. Also, we can use couplers for input and output of optical signals between fibers and silicon photonics devices. Furthermore, photodetector diodes and MOSFETs can be used in silicon photonics. By using MOSFET, we can implement control blocks in the silicon photonics chips. Unfortunately, we can't use laser device in general silicon photonics. Therefore, external laser device is needed for silicon photonics devices. This slide shows structure of the optical waveguide in silicon photonics. This figure is a cross-section of light traveling direction. Refractive indexes of silicon and silicon oxide are 3.47 and 1.44 respectively. These values are different to each other. Light is fully reflected at the boundary between silicon and silicon oxide, like this figure, full reflection here, full reflection here. So light is traveling inside the silicon waveguide. This figure shows a cross-section of another direction. In order to fabricate optical wave structure like these figures, SOI CMOS-based semiconductor technology are required for silicon photonics. The loss of normal optical fiber is 0.2 or 0.4 dB per 1 kilometer. It is very small loss. The loss of optical waveguide in silicon photonics is 2 or 3 dB per 1 centimeter. This loss is extremely larger than the optical fibers, but it is acceptable because lengths of the optical waveguide in silicon photonics are very, very short. Okay, this slide shows typical block diagram of an optical transmitter and receiver using silicon photonics. Transmitter and receiver. Firstly, an optical signal without a modulation is provided from an external laser device, here. It is input in silicon photonics transmitter via this coupler. And the light signal is traveling in the waveguide, optical waveguide here. The light signal is modulated in this modulator, and this modulator is controlled by an electronic controller using MOSFETs. And the modulated signal is output via this coupler to the optical fiber. Next, modulated signal is transmitted to the silicon photonics receiver via this optical fiber. The signal is input to the receiver via this coupler, and optical signal is converted to the electrical signal in this photodetector. After that, electrical signal is demodulated by the electronic demodulator using MOSFET. In this slide, miscellaneous information about silicon photonics is shown. You can obtain technical information about silicon photonics from international conferences such as ISSCC IEDM, OFC, and so on. There was a very good tutorial about silicon photonics at ISSCC 2021, last time ISSCC on last February. And OSC is one of major conference in the optical community. It is very, very big international conference. And you can use silicon photonics foundry such as AIM, AMF, and global foundries, and so on. Unfortunately, I have not used these silicon photonics foundries yet, but cost of shuttle of silicon photonics is much lower than that of advanced CMOS processes. Okay, sorry. Now let us move to the electrical topics. Electrical communication networks are also categorized by the communication distance as shown here. Major electrical wireline communication standards such as PCI Express and CXL are categorized in the long reach or medium reach. The shortest one is the ultra short reach USR. A communication distance between is only less than 1 centimeters, and it is used for between two chips on the same package. It is clear that the communication with shorter distance needs lower power consumption. This slide shows losses of transmission line with different lengths. This is a loss of longer transmission line, and this is a loss of the shorter transmission line. As shown in this figure, longer transmission line has a larger loss under the constant bandwidth. The loss of shorter transmission line is here, and loss of the longer transmission line is here, and larger loss is here. When we need higher data rate operation using wider bandwidth, the loss of the transmission line is also increased as shown here. The loss of normal data rate is here, and loss of high data rate is here. There are very large loss for the higher data rate. This loss of the transmission line have to be compensated by using equalizers. And equalizing is one of key techniques for wireline communication systems. This slide shows equalizing technique using wireline transceiver. This figure shows response for loss of the transmission line between transmitter and receiver. The loss becomes larger and larger in high frequency region. These losses are compensated by equalizers. An ideal frequency response of equalizer is like this. The loss is completely compensated by the ideal equalizer, and frequency response after ideal equalizer is flat like this. Actually, the frequency response of ideal equalizer like this cannot be realized. Frequency response of actual equalizer is like this. and the frequency response after actual equalization is not flat as shown here. So it is challenging to compensate the loss for very high data rate signal even using equalizer. There are two equalizing architecture for receivers. One is analog-based architecture shown here, and the other is an ADC-based architecture shown here. In the analog-based architecture, a continuous time linear equalizer, CTLE, and decision feedback equalizer, DFE, are in the analog domain. The equalizing performance of analog-based architecture is not so bad, and power consumption is low. So analog-based architecture is suitable for low data rate or short communication distance applications. On the other hand, the ADC-based architecture has equalizers in both analog and digital domain. The continuous time linear equalizer, CTLE, is in the analog domain, and decision feedback equalizer and feed-forward equalizers are in the digital domain. The equalizing performance of ADC-based architecture is high, but power consumption is also high. So the ADC-based architecture is suitable for high data rate and long communication distance application. Actually, the latest receiver for 112 gigabits per second Ethernet adopts the ADC-based architecture. It is because the loss compensation using equalizer is difficult in such high data rate. And this table shows data rate trends for PCI Express. Basically, maximum data rate was increased by using wider bandwidth, like here. And NRZ signal, like this waveform, is used until PCI Express Gen 5 here. But PAM4, for labeled pulse amplitude modulation, like this waveform, will be used in PCI Express Gen 6. The PAM4 electrical signal will be adopted up to 128 gigabits per second, but I think there is some possibility to adopt optical technologies for 256 gigabits per second data rate in Gen 8. So I think for the medium and long reach applications, electrical interfaces are replaced by optical interface in future. But electrical interfaces will be remained for short reach applications such as ultra short reach. The final topics is co-packaged optics, CPO, in optical switches. CPO was one of hot topics of the major optical conference OFC in this year. The CPO is used in optical switches as shown in here. Firstly, an input optical signal is converted to an electrical signal by using this silicon photonics chip. After that, electrical signal is switched to the proper destination by CMOS switching LSI by here. Finally, switched electrical signal is converted to an output optical signal here. In the past, electrical to optical signal converter using silicon photonics and the switching LSI using CMOS technology is in individual packages, as shown in here. So relatively long transmission line is needed to connect two packages here and here. Furthermore, high data rate signal is traveling in both PCB and package boards. Therefore, high-cost boards are needed for both PCB and package boards. On the other hand, in CPO, two chips are in the same package, as shown here. So the transmission line between two chips is very short, and it is closed in the package. Therefore, we can use low-cost boards for the PCB because there is no high data transmission line on the PCB. So we can achieve low power and low cost optical switches by using CPO. Next, let me present our work about bridge chips for high bandwidth and large capacity storages. This slide shows a typical configuration of solid-state drives, SSDs. High-speed serial interface such as PCI Express is used between an external CPU and SSD controller here. DDR interface is used between the SSD controller and DRAMs here. Toggle DDR interface is used between the SSD controller and NAND flash memories here and here. We have developed special interface using bridge chip between the SSD and NAND flash memories. This slide shows issues for large capacity and high speed SSDs. To achieve a large capacity, large number of NAND flash memories are required, like this. When large number of NAND flash memories are connected to one channel of toggle DDR interface, like this figure, operation speed is degraded by large load of many number of NAND flash memories. To improve the operation speed, number of channels should be increased like this figure. In toggle DDR, 12 high-speed wire lines are needed for one channel toggle DDR interface. In this case, too many number of high-speed wire lines are connected to SSD controller and they cannot be laid out on PCB near SSD controller. As shown in this slide, there is trade-off between large capacity and high-speed operation of SSDs. To improve the trade-off in the previous slide, bridge chips are used like this figure. In this figure, B means bridge chip. Interface between a SSD controller and bridge chip and between bridge chips. are high-speed serial interface using palm hole. By using serial interface, the number of high-speed wireline is greatly reduced, only 4 in this case. And high data rate operation is achieved by using palm hole. Also, daisy chain configuration is used. The bridge chips are connected in series like this figure. It is effective to increase the total capacity of the NAND flash memory. Therefore, we can achieve large capacity and high-speed operation by using these bridge chips. This slide shows chip micrograph of the bridge chip and measurement setup. The bridge chip has been fabricated using 28 CMOS process. We have mounted one bridge chip on one evaluation board here. We use 6 evaluation boards for measurement. These boards are stacked using stacking connector like this photograph. 2 evaluation boards are used for a transmitter and receiver in the controller, and 4 evaluation boards are used for bridge chips like this figure. The evaluation board at the bottom here is a transmitter for the controller, and top one is used for the receiver of the controller. This slide shows measured result of the bridge chips. Firstly, the palm hole signal transmitted from transmitter in the controller to the receiver of the first bridge chip here. Next, transmitter of the first bridge chip B0 transmit the palm hole signal to the receiver of the next bridge chip B1. Such operation is repeated for the third and fourth bridge chips, and finally, the palm hole signal is received by the receiver in the controller here. As shown here, clearly opened eye or palm hole signal are obtained at the bridge chips and the final receiver in the controller here and here. And as shown in this figure, good measured bit error rate curves are also obtained for the first bridge chip and final receiver for the controller. These measured results indicate our bridge chips in the daisy chain configuration are correctly operated. This slide shows measured results of our recent work for the bridge chips. The data rate has been increased up to 56 gigabits per second. This figure shows measured output palm hole waveform with the transmitter. The widths of eyes are narrow, but they are clearly open. This figure shows measured detected palm hole waveform of the receiver. In this receiver, we have implemented an on-chip oscilloscope. We can observe such waveform like this. So we have developed the bridge chip for large capacity and high bandwidth storages up to the 56 gigabits per second operation. Okay, next, let us move to the topic of an issue of low-cost PCB such as FR4. It is serious problem for differential circuits. This photograph shows a fabricated PCB for measuring transmission lines. This figure shows a typical design artwork for measuring measuring differential transmission lines. It has input and output patterns for contacting by high frequency probes like this. This picture shows actual measurement system. This is a PCB under test. This one and this one are high frequency probes, and it is network analyzer. Measurement conditions for network analyzer are shown in this table. In this time, we have measured transmission lines up to 67 gigahertz. Again, this photograph shows our PCB. We have put multiple test elements using same design artwork at the red marked position here, 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 and so on. The design artwork of these test elements are completely the same on the CAD design, and only location of the PCB are different. Some of them are tilted like this. Now, I have one question to you. Do we obtain similar measured result for these differential transmission line with the completely same design artwork? What do you think? I think some people know the answer. The answer is no, unfortunately. This slide shows measured results for these test elements. We have measured two kinds of PCB, namely backdoored board and built-up board. These measured results shows different insertion gain SDD21 and differential to common mode conversion gain SCD21 respectively. As shown in these figures, the measured results show large variation for both kinds of PCB. Here, SCD21 is strongly correlated with electrical symmetry of the differential transmission line. In ideal case, namely, differential transmission line is completely symmetry, a differential input signal is output as a differential signal completely, and no common mode signal is output. So, ideally, SCD21 is not appeared. Thus, this measured variation of SCD21 means that degradation of electrical symmetry is caused by the location of the test elements. This slide shows measured SDD21 and SCD21 for the tilted test element like this. It is obvious that SCD21 for 0 and 90-degree tilted test elements are large, and SCD21 for 30 and 45-degree tilted test elements are small. This result means that electrical symmetry of the 30 or 45-degree tilted transmission line are good. This page shows calculated eye diagram of output common mode and differential component for 0 and 30-degree tilted transmission line using measured S parameters. In SCD21, that 30-degree tilted transmission line shows very good response, and there is no common mode output in the time domain like this. On the other hand, the 0-degree tilted transmission line shows big common mode output like this. Why we made such large electrical asymmetry in the 0-degree tilted differential transmission lines? The answer is in this slide. It is known that the mechanism of location and direction dependence is due to the positional relation between the glass cloth and signal conductor. The cross-sectional micrograph of the differential transmission line are shown here. It is a little difficult to see. The glass cloth is here and here, and copper transmission line is here and here. This glass cloth, this one, is welt, and the warp of the glass cloth is here, around here. A simplified picture is shown here. The position of glass cloth is changed periodically, as shown in here. Overstructure of glass cloth is shown here, like this. The warp and welt of the glass cloth are interwoven two-dimensionally, like this figure. In the case of 0 and 90-degree tilted transmission line, copper transmission lines are parallel or orthogonal with the warp and welt of the glass cloth. So asymmetrical relation between the glass cloth and two copper transmission lines is kept every place in the copper transmission line. On the other hand, in the case of 30-degree tilted transmission line, effect of the glass cloth are averaged, and good electrical symmetry can be obtained. The positional effect of the glass cloth have been modeled for using electromagnetic simulation, EM simulations. The periodic structure of the glass cloth are modeled as shown in this figure. By using this model, performance variation are successfully represented by using EM simulators. This slide shows EM simulation result for 0 and 30-degree tilted differential transmission lines. The glass cloth model shown in the previous slide is used, and distance between the two transmission lines are changed in the EM simulator. For the 0-degree tilted transmission line, the variation of SDD21 is large, and the variation and values of SCD21 are also large. On the other hand, for 30-degree tilted transmission line, the variation of SDD21 are small, and the values of SCD21 are also small. These simulation results are similar to the measured results. Thus, it has been confirmed from both measurement and simulation that the 30-degree tilted transmission line is robust for the positional dependence on PCB. Although we can represent the effect of the glass cloth using EM simulator, actually we cannot know the accurate position of the glass cloth in our PCB. So one limited solution is to use the tilted line, but perhaps we cannot design only using tilted lines. Another easy solution is to use high-cost PCB with a flattened glass cloth. Okay, next let me present our future works briefly. It will be a good summary of my today's talk. This is content of our future work. The first item is high bandwidth, large capacity, and low power NAND flash memory module. We are developing it as a national project supported by New Energy and Industrial Technology Development Organization, NEDO. NAND flash memories and memory controller, including bridge chip, will be mounted on the NAND flash memory module. Data rate of daisy-chain bridge chips is increased to 128 gigabits per second. It is a very challenging target for us. Accurate models for PCB and packages are also developed to minimize power consumption of the bridge chip. The second item is an optical SSD in 2030. It is just started, and we are considering about the requirement of SSD in a disaggregated optical network. Let me present these two items briefly. This slide shows background of national project. In order to store big data in the NAND flash memory module, large capacity is required. Also, in order to read big data quickly from NAND flash memory module by processors such as CPU, GPU, FPGA, and accelerators, high bandwidth is also required. To realize large capacity, daisy-chain technique is used, and accurate PCB and package model are developed for low power bridge chip with daisy-chain configuration. To hide delay of the NAND flash memory, prefetch is used, and high-speed NAND interface is also developed. This slide shows NAND flash memory module under development. Many number of NAND flash memories are mounted using daisy-chain techniques for achieving the large capacity. High bandwidth is achieved by using serial interface between processors and the memory controller here, and 128 gigabits per sec daisy-chain configuration here. This slide shows a method to achieve low power consumption. The distance between two memory controller is assumed to be 3 or 10 centimeters. It is relatively short distance, but data rate of 128 gigabits per second is very high, so accurate PCB and package model are needed. First, we will measure and characterize PCB and package, and the accurate model for them are extracted. By using the accurate models, we can design the PCB and package which have a minimized loss. At last, per consumption of daisy chain transceiver can be reduced under low loss PCB and packages. Okay, let's move to the final topic of optical network. And now Kioxia is one of sponsor member in the Innovative Optical and Wireless Network Global Forum, ION. The founding members are Intel, NTT, and Sony. 22 companies, including Kioxia, are sponsor members, and 40 companies are general members, and 9 organizations and universities are academic and research members. Now we are discussing with ION members to achieve low power, high bandwidth, and low latency using optical technology in 2030. We welcome your join to the ION Global Forum. This slide shows conventional and future network architecture. In conventional server-based architecture here, if you need more resources for the network, you will add a new server. But utilization efficiency is not high because if you need add only SSD, but CPUs and GPUs in the same server also added at the same time. To enhance the utilization efficiency, disaggregated architecture is adopted here. By using disaggregated architecture, flexibility to add resources is improved, and you can add only SSD if you want. Actually, the disaggregated architecture has already been introduced using electrical technologies. Now, we are considering about requirement for the NAND flash memories and SSDs in the disaggregated computing using optical technology in 2030. Okay, let me conclude my talk. We are developing daisy chain transceiver to achieve high bandwidth and large capacity storages with low power consumption. PCB and package models are important to reduce power consumption of the transceiver. In 2030, optical technologies will be introduced for low power, high bandwidth, and low latency communication. The NAND flash memory module is developing as national project supported by NEDO. Thank you for your kind attention. Merci.
Thank you very much. And it's very interesting and wonderful subject and research topics. And now, let's move on question and answer time. If you have any question, please into some check your name to chat space.
I have put a question.
Please.
So this is a question for the speaker. Do you think that PAN 8 can be investigated to increase the data rate? Are we reaching a limit of feasibility?
It is a very good question. PAM 8 is very attractive for high data rate, but SN specification of SN is very, very severe. So I think it is difficult to apply next generation communication.
Thank you. Any other question?
We have one question here in Bordeaux.
Yes.
Yeah, hi. I have a question about the technology. How do you see the future developments in terms of moving forward in more advanced technologies, going into deep, ultra deep technology like 7 nanometers and 3 nanometers and so on?
Yes, it is a very good question. For 112 gigabits per second transceiver for Ethernet is developed by using 7 nanometer FinFET process. Now we are developing 128 gigabits per second transceiver for our project. We will use 5 nanometer FinFET technology. So it is difficult to say, but I think we can't realize next generation transceiver such as 256 gigabits per second transceiver using electrical technology. So I think transceiver of over 200 gigabits per sec should be designed using optical technology. It is okay for you?
Thank you.
Thank you. And any question from Bordeaux?
I think we are approaching the end of this session as we need to switch to the session A.
Yes. Thank you. Time. Thank you very much, Dr. Fujimoto. Thank you very much.
Thank you.
Thank
Merci.
you. Thank you. So I invite everyone to switch now on Zoom for the session you would like to attend. See you very soon in the Zoom rooms.